Hey pre-calc students, this is Unit 8, Day 7. Today we are concentrating on finding all of the roots. So if you want to start your notes and get this written down, we're going to be talking about how do we find the roots of an x squared equation, x cubed, x to the fourth, x to the n power, and how we can use some of the tools from Unit 8 to be able to help us with that. But before we do that, you actually, as you're finding your paper and getting yourself set up there, don't have to copy down what I'm about to show you, unless you feel like you want to include it in your notes. It's completely up to you. But I'm going to have us think about a question from a different perspective and a way we would have solved this at the beginning of our course. So find the 3 cube roots of 8. So notice how I have pluralized here, not just the cube root of 8, but the 3 cube roots of 8. So there are 3 answers to this. And if you might be thinking about, well, hey, I know what the cube root of 8 is. The cube root of 8 is 2. You are correct, but we'll talk about what that implies in a second. So we'll start by setting this up by saying x equals the cube root of 8, which you're right is 2, but 2 is what we call the principal root. It's the first solution we get when we take the cube root of 8. We talked about principal root in the lesson from yesterday. Well, here's another way to think of it, though. To get the 3 answers, you can cube both sides. That's how I got to this step. And again, you can just sort of follow along with me if you'd like to. And then x cubed minus 8 equals 0, so set it equal to 0. And the way we can solve this is we have a few different techniques. But one way might be by factoring. This is the difference of perfect cubes. It's been a while since we've seen that factoring technique, but hopefully you'll remember it looks something like this. You take the cube root of each of those terms, and then you square this, middle multiply, square that. There's a whole pattern for the signs, which we will review very shortly when we start getting ready for a midterm. But this is what it would factor into according to the difference of perfect cubes. So wait, hey, here's that x equals 2 solution when I set that equal to 0. So that's definitely something we'll see. This quadratic, unfortunately, is not factorable. So you would have to use quad formula, or for those of you that love complete the square, you can go ahead and do that. But the other 2 solutions happen to be complex, a plus bi answers, -1 plus or minus I radical 3. And again, that would be a result of either quad formula or CTS. So what I want you to think about is, what are these solutions in cis form, or that polar form we've been working with throughout this whole unit? So I'm hoping 2 is kind of easy to visualize, right? 2 would just be 2 to the right, so that's going to be 2 cis 0. But for the other 2, you might have to draw a picture and set those up, right? -1 plus I radical 3 is in quadrant 2. -1 minus I radical 3 would be in quadrant 3. And if you set those up and convert, I'm trusting your converting skills at this point. This is what the 3 answers look like in polar form. 2 cis 0, you would also still get 2 cis 120 and then 2 cis 240. So perhaps in polar form, something you recognize right away is that those R values are all the same. And that is true every time you go to solve an equation like this. But what I want you to think about is what's going on with those angles there. So is there a pattern with these particular polar solutions? Why might our 3 solutions be 120 degrees apart? So if you didn't notice that, you would add 120, and then kind of go from there. Well, first of all, the reason why we call this polar form is that when we eventually go to start taking a look at these graphs, a polar graph has a bunch of concentric circles that we graph within. So think about if you were standing at the North Pole and looking down at the lines of latitude, there would be these concentric circles branching out from the top, which is the North Pole there. So it has something to do with the fact that in a polar world, we're looking at things that involve circles. So think about maybe our 3 solutions being 120 degrees apart and how that all fits. All right, now we can kind of go back here to the notes. This is where you can start writing down again. And take a look at x squared. So x squared, think about it, when you solve an x squared equation, there are 2 roots. And what I want to talk about is for those 2 roots, how many degrees apart would my polar or my cis solutions be? Well, as it turns out, for the x cubed equation we solved, which had 3 roots, we saw that they were 120 degrees apart. And where does that actually come from? It's because if you take a total circle, 360, and divide by 3, that's where you get 120. So as it turns out, the number of degrees apart your polar solutions will be is 360 full circle divided by the number of roots. So your solutions will always be equally spaced within a circle. So now if I use that same rule and come back up here, 360 divided by 2, would mean that the solutions are 180 degrees apart if we're solving a quadratic equation. And then, of course, we can keep building here that if I have 4 roots, those solutions would be 360 divided by 4, which is 90 degrees apart. And in general, if we're solving something even higher than a 4th degree polynomial, which has n roots, you would take 360 and divide by n, and that's how many degrees apart the roots would be. So we're going to take that concept today, and we're going to go ahead and apply it to solving a series of equations. Equations that we couldn't really find the solutions for, thinking back to, like, remember Descartes' rule of signs? And remember all that stuff with rational root theorem and stuff like that? It's been a while since we've done that. But consider this x to the 4th plus 16 example. We know that this has 4 roots, because a 4th degree polynomial has 4 roots. If I asked you how many degrees apart they are, we can kind of cheat and look up here and see it's 90, but you always just take 360, divide by the number of roots. And I know that my solutions in the end should be 90 degrees apart. Now, I'm going to give you a real big throwback for 1 second here and remind you that if we were to use something called Descartes' rule of signs, this is good review for the midterm. In f of x, the signs are positive and positive. And then we do something called f of negative x, which means if I plug in a negative x here, but wait, raising it to the 4th power would keep it positive, and the 16 is positive. Then we would set up a little chart for the positive, negative, and complex cases, and there were no sign changes in f of x or f of negative x. However, I know that this has 4 roots. So all 4 roots of this have to be complex. And this was a possibility looking back to Unit 4b, which is when we learned how to do this. But we said, you know what, in this unit, we can't solve for all 4 complex roots. Now we have the tools to do that. So let's go ahead and walk through the process today and see what that looks like. So to get started, you have to isolate x. So in this example, x to the 4th plus 16 equals 0. To get x alone, simply subtract 16 to the other side. Not a scary step. Then to continue getting x alone, if you're raising it to the 4th power, let's take the 4th root of both sides. So we get x equals the 4th root of negative 16. Now, you may think you know what the 4th root of negative 16 is, but if you look back at yesterday's notes, it turns out it's not as simple as it looks. You must convert this into polar form before you go ahead and decide what the 4th root of negative 16 is. By the way, this is just going to be the principal root, the first solution that we get. Negative 16, I'm not going to draw the picture because I'm hoping you're okay with it, would be 16 cis 180. And now we can actually apply Dumont's theorem and figure out what is that principal root, what is that first solution. So this would be the 4th root of 16, and then 180 would get multiplied by a 4th or divided by 4, however you want to think about that. Because this is the first solution, I'm going to write my first answer as x1. And x1 is, let's see, the 4th root of 16 is 2. Cis 180 divided by 4 is 45 degrees. So given that that's our first solution, again, this is called the principal root. You don't have to necessarily look too much into that other than knowing it's our first solution. We said that there are 4 solutions total. So we need an x2, an x3, and an x4. And if we think about the patterns that we saw in that other example that we started with today, we know that for the other 3 solutions, it's going to be 2 cis something. And what are those angles that it's going to be cis of? Well, as it turns out, this was an important piece up here. The roots are 90 degrees apart. So if you add 90, the next angle here would be 135. And that's actually a nice angle, so we like that one too. If you add 90 again, you'll get to the third solution, which is 2 cis 225. And last but not least, add 90 one more time to get to the fourth solution, which is 2 cis 315. But oh wait, we're not even done yet, because now we have to take those 4 answers and convert. I could just hear the sighs coming from your screen on the other side. Like, oh man, we have to convert all those. It's not as bad as it looks. Because here's the deal. If I draw 2 cis 45, which is this triangle right here, this is the weird pattern with the 45 where this would be 1 radical 2 and 1 radical 2. So I understand that that part's weird. Your first answer is radical 2 plus I radical 2. But if I go to do 2 cis 135, isn't it the same picture but just in a new quadrant? It's in quadrant 2, hypotenuse is 2, reference is 45. And the same thing would apply for the 225 and the 315. It's the same exact triangle in all 4 of the quadrants. So just think about if I'm in quadrant 2, I'm going left and up. So that's negative radical 2 plus I radical 2. Quadrant 3, the 225, you're going left and down. Negative radical 2 minus I radical 2. Finally, quadrant 4, right and down, so that's positive, and then down is negative. Radical 2 minus I radical 2. These are the 4 complex roots that we never knew how to solve for back in Unit 4B a long time ago. These are the 4 solutions to this equation. X to the 4th plus 16 equals 0. So we'll probably need a few more of these under our belt to feel really confident with the process, but that's what this whole unit is building up towards. Solving for all of the roots, even when all 4 of them happen to be complex. So let's do another one. Let's take a look at the example x cubed. And the weird thing about this next example is that I'll even throw in some i's in the equation to start. So x cubed minus 27i equals 0. So I know that looks a little strange probably to see I mixed in with the coefficients of this cubic, but we're going to solve it just like we did in the last example. So first things first, let's get x alone. So add the 27i to the other side. And then take the cube root of both sides. It's really tempting at this step to say, you know what, the cube root of 27i is 3, I don't know what the cube root of I is. Turns out it's because we have to convert this first, just like we did in the last one. Convert that over to polar form. Well, 27i would just be going up 27, so the angle there is 90. 27i converts to the cube root of 27 cis 90. So we got x alone, we converted to polar form. Your next step to get your first solution, the principal root, is apply Demoivre's theorem. Take the cube root of 27, that's 3. And then the angle gets divided by 3. 90 divided by 3 is 30. So we got 3 cis 30 for the first solution. But oh wait, I never even said for this one how many roots we should have. Well, x cubed definitely has 3 roots. But keep in mind, if you do 360 divided by 3, they are 120 degrees apart. So you're going to add 120 to this. That's going to give you your second solution, x2, which is 3 cis 150. And finally, just add 120 one more time because we only have 3 solutions. The third solution is 3 cis 270. And then the last step is take your 3 answers in polar, convert them back to rectangular. So remember in the last case we had that one triangle that just applied to all 4 quadrants? That's not exactly the case here, but I'll tell you the first 2 use the same picture, just in quadrant 1 and quadrant 2. So 3 cis 30 and then 3 cis 150, they're the same triangle, same reference angle. So we can use that to convert, I think, both of these. If 3 is the hypotenuse, 3 halves goes here. And then 3 halves radical 3 would be on the base there. So 3 cis 30 would be 3 halves radical 3 plus 3 halves I. If you want to complete a whole nother picture, that's fine, but I think I can use the logic that I'm just going to go left and up those same dimensions. So this is negative 3 halves radical 3 plus 3 halves I. And although you might be annoyed that I can't use that picture for the last one, 270 is a nice one just because it's quadrantal. It's right on the border like this. And if I'm 3 in that direction, going 3 down, the answer would be negative 3i. And that's the final answer. So these 3 solutions are the 3 complex answers to this original equation. So this is kind of an intense process, but I promise you over the next 2 days, actually, we'll be doing more practice with solving for all the roots just like this. These 2 examples are just a little bit of a taste as to what's coming up, but If you have any questions about that, let me know next time we're together. Otherwise, have a great rest of your day.